And next up we have Michal Křížek, Czech Academy of Sciences, and his talk is, he's talking about should philosophers rely on the epistemic authority of the principle of relativity.
Okay, so good afternoon, ladies and gentlemen, dear Mr. Chairman. I will speak about some problems which I found in the theory of relativity. And first of all, I would like to thank organizers for inviting me here, also to Tuomo Suntola, Avril, and Petri Leivonen. Okay, so I am from Prague, and Prague stood at the birth of two revolutions in building the theory of gravity. At the beginning of 17th century, Johannes Kepler formulated there his first and second law about motions of planets. The third law was discovered later when he was not in Prague. And he used some very precise observational data of Tycho Brahe. And this then helped in the formulating of a Newton theory of gravitation. In Prague, you can find many plaques dedicated to Kepler. These are not all. There was also Kepler Museum. Unfortunately, there were no money in the city hall to support this museum, so now it does not exist, which is a very pity, because Kepler was genius. And the second was Albert Einstein, who worked in Prague in the beginning of the 20th century, and he received his first full professorship at Charles Ferdinand University in Prague. And his colleague, Georg Pig, worked on non-Euclidean geometries, yes? And he taught Einstein the foundation of tensor calculus in Prague. So Einstein found in Prague calm atmosphere necessary to formulate the basic ideas of his general theory of relativity. And he wrote also 7 important papers on general relativity and similar topics. And I was fascinated by his theory, so I co-organized in Prague this plaque, which is in the Old Town Square. Here you can see our sun, and there is a star, an observer, and if there is this light going from star to observer, it is slightly bended, and this was one of the, main achievements of the theory of special relativity. So I admired approximately 30 years general relativity. It is very beautiful theory, really very beautiful theory. But later I found that there are some drawbacks, and I will now tell you more about these drawbacks. So they will be contained in my presentation. So I am arguing that the theory of relativity should be replaced since it has several really serious problems. So naturalist philosophers should not be overly confident about general theory of relativity. And I am approaching these problems from the viewpoint of the principle of relativity, which together with the constancy of the speed of light is the heart of relativistic physics. And I will present 3 real-life examples where the relativity principle does not hold in the physical universe. And of course, the problems which are now which I will formulate in special relativity, they will also imply that there are problems in general theory of relativity and also standard cosmological model, which is now called lambda cold dark matter model. So very briefly about special relativity. So special relativity is based on two following postulates. The first postulate is called the principle of relativity. The laws of nature are the same in all inertial frames. So this allows any observer to be considered as the state of rest. Yes, this is very important. Yes, every observer may think he is at rest. Therefore, it is relativity. Therefore, it is called theory of relativity. And the second postulate is that the speed of light is the same in all inertial systems. Know that Albert Einstein didn't perform any physical experiments. It was only, he made several thought experiments with trains traveling at high relativistic speeds in railway stations and so on. But however, one must carefully distinguish between a train in a special theory of relativity mathematical model and a real train. These are completely two different quantities. So now Tuomo was quoting the first, one of the first sentence from the Einstein's paper. I will quote also from the first page of his paper where he speaks about the principle of relativity. So this is a paper which appeared in 1905, and Einstein on the first page writes, "We will arise this conjecture, the support of which will be hereafter called principle of relativity, to the status of a postulate." Postulate, this is something like axiom in physics. This means this is a statement which shouldn't be which shouldn't be somehow which should be considered to be valid, yes? And then there is second postulate that the light is always propagated in empty space with a finite velocity c, independent of the state of motion of the emitting body. So these two postulates form the basis of the special theory of relativity. So this is so I will repeat once again. The postulate is a statement that should not be disputed, but its meaning may vary, of course. It is something like an axiom in mathematics. Now it is generally accepted that the principle of relativity describes the actual physical universe very well. And this hidden assumption is considered to be obvious. However, below we shall see that the principle of relativity does not hold in the physical universe for high velocities, yes? The principle of relativity and the light postulate imply time dilation and length contraction effects. So concerning time dilation, from the perspective of a stationary observer, and as an inertial frame moves faster, the duration of 1 second on that frame appears to be lengthened. Consequently, time passes more slowly in the moving inertial frame. This leads to the famous twin paradox, and the clock at rest is the fastest. Yeah? So if you have a clock, and if it moves, then the time goes slower. Yes? But I would like to point out here that the notion of observer is a little bit confusing in theory of relativity, because I have my watch here, and if this watch will be approaching me, then I will see higher frequency, not lower frequency as special relativity predicts. I will see higher frequency because there is Doppler phenomenon, and Doppler phenomenon is much stronger effect than time dilation. Yes, so we must this take into account. Second is length contraction effect. So from the perspective of stationary observer, as an inertial frame moves faster, the length of 1 meter in that frame appears shortened. So I have 1 meter, say, bar, and if it moves by very high relativistic speed, then it is shorter, maybe half a meter only. Yes? And it is expressed by this formula, which is here. Maybe, no, there is only one formula. So this gamma, this is the so-called Lorentz factor. It is number which is always less or greater or equal than 1. So it can be, for instance, 2 or more. It can be, in fact, arbitrarily large number. So L0 denotes this length and 1 meter, for instance. And if gamma is, for instance, 2, then the length in the moving system must be shorter. Yes, it must be, for instance, half a meter. So the bar at rest has the greatest length. For the time being, there is no physical experiment which would demonstrate length contraction, yes? I really do not know any. So now I will present a few examples, 3 examples. So according to the principle of relativity, all frames are equivalent. This means that the observer is not able to distinguish whether he is in rest or if he moves, yes? So now assume that we have a very fast-moving observer, for instance, 5% of the speed of light or 50% of the speed of light. And on the left, you see, for simplicity, a uniform distribution of some spherical objects. And according to the length contraction effect, a fast-moving observer which sits at the origin of this picture which is on the left. So he will see all spherical effects deformed. It will be not anymore spheres, but it will be some ellipsoids. He will see ellipsoids, yes? And these blue dots can be planets or stars or globular clusters or galaxies, whatever. Einstein, of course, didn't know that there are some galaxies. Yes, they were discovered by Hubble 20 years later. So now it contradicts to special theory of relativity because, especially to the principle of relativity, because this fast-moving traveler which sits at the origin of this right system, yes, so he will see that he moves because all objects around him will be deformed. So he cannot think he is at rest. He just can fly in arbitrary direction, in arbitrary distance, in arbitrary speed, yes? Whatever he chooses, if he travels very fast, he will find that all objects around him are elliptical. So he's not at rest. So this is first, drawback. So theory of relativity contradicts itself. This is continuation of this example. This fast-moving traveler will see that all galaxies in front of him will be shifted, the light will be shifted to blue colors, and the galaxies behind him will shift the spectrum to red colors. So in this picture, because I cannot draw the celestial sphere on plane, so this is projection very famous projection. So the fast-moving traveler will see one half of the spherical celestial sphere shifted to blue colors, and behind him to red colors. So he again, if he travels fast, he is not at the rest. So this is first example. So the principle of relativity, I'm sorry, but the principle of relativity does not hold in the physical universe. Einstein, of course, could not have known about the existence of galaxies and everything. He assumed that everything is in vacuum. Vacuum is only, say, hypothetical term which has nothing to do with real universe. Which are the main problems of general theory of relativity? The extreme complexity of Einstein equations. They are written here in only one line, but if you rewrite it, then there is Ricci tensor. It depends on the so-called Christoffel symbol. Christoffel symbol depends on metric tensor. And if you rewrite it in components, you get several pages of equations. And I work for 50 years on numerical solutions, partial differential equations, but this system is so complicated that it cannot be compared to Navier-Stokes equation or Maxwell equation and so on. Einstein equations do not allow us to prescribe reliable initial conditions except for some academic examples. They do not also enable us to prescribe boundary conditions. The modeling error of Einstein equations is not known in general. The metric tensor, which is this Gij, does not uniquely define the geometry of the corresponding space-times manifold. There is extreme computational complexity of numerical, of the numerical solution of Einstein equations. Moreover, up to now, nobody knows the exact solution, this means analytical solution of Einstein equation for two bodies. For one body, it was derived by Schwarzschild or Kerr, but for two bodies, nobody knows the analytical solution. Therefore, we do not know the error of Einstein equations. There is problem of Mercury perihelion shift because it is a completely ill-conditioned problem. The composite Schwarzschild solution, which is, if you take Schwarzschild solution inside our sun and outside, they cannot be smoothly connected. They can be continuously connected, but there is jump in first derivatives, but Einstein equations are second-order equations. And classical tests of general relativity do not imply the Einstein equations. Yes, this is opposite mathematical implication. There are, of course, many problems from the also in the actual cosmological model, because cosmological model was derived from Einstein equations, and Friedman did it. Friedman used a lot of symmetries of this three-sphere, and in fact, Friedman equation, this is only ordinary differential equation of the first order, is nothing else than Einstein equations considered in a special case. And this Friedman equation implies the existence of dark matter. We do not know what is that. I know this is a modeling error. The existence of some hypothetical dark energy. Nobody can explain large angular momentum of all spiral galaxies, because at the beginning the universe was homogeneous, isotropic, and now there is a lot of energy hidden in all spiral galaxies because they rotate. There is a problem of setting some accurate initial conditions. in the neighborhood of our sun, there are stars which are older than 14.5 gigayears, whereas according to Einstein equations, our universe is only 13.8 gigayears old. The cosmological model admits division by zero, which I'm a mathematician, yes, but division zero, it is absolutely impossible, yes, in theory. There is problem of cosmological constant. Yes, Einstein introduced cosmological constant, but up to now, nobody knows any significant digit of cosmological constant, any significant digit. Can you imagine that mathematicians would write some thousands of papers about constant and they wouldn't know any exact digit? This is just very, I would say, sad story. Flatness problem. At the time, nowadays, cosmologists believe that our universe is flat. This means infinite, but I have personally very big problems with infinite say universe. There is 120 order of magnitude discrepancy between measured and theoretically derived density of dark energy. Yes? If there would be, say, one order difference, that I would be able to discuss with somebody. But if it is 120 order difference, then there is no discussion. And the Big Bang problem itself is against, say, principle of causality, yes. And the list goes on. I was so, say, frustrated that I wrote a book in Springer. It took a lot of effort to finish it because we had 4 strong reviewers, but after some time we succeeded. Here I listed only 10 or 20 problems, but there are about 100 problems about cosmological model. Now I will present other drawbacks. So when I was dealing with cosmological model, I supposed that the main problem that it does not correspond to observation is that we do excessive extrapolations of Einstein equations to the whole universe, yes? Because you cannot apply, for instance, Archimedes' law to the solar system. If you would apply it, then you get no-sense results. Also, if you would apply Archimedes' law to scales of 1 angstrom, you would also get completely no-sense numbers. So every, say, law has some scale where it is good approximation of reality and where it is not a good approximation of reality. But Einstein equations were, say, derived or were tested on the scales of the solar system, and then Friedman applied to the whole universe, which is at least 15 orders bigger than solar system, yes? So it is, we cannot apply, even I think that we cannot apply Newton's law to the scales of, say, galaxies or cosmological distances. So I will present now further examples. So, in 1964, Taylor and Penzias, Penzias and Wilson, they discovered cosmic microwave background. I think that you have seen this picture, which is quite often in various journals. And they found that each cubic meter of our universe, each cubic meter, yes, here, contains approximately 400 millions of relict photons. 400, but it is everywhere. You cannot avoid it. It is just. And this corresponds to the temperature approximately 3 kelvins in all directions. Yes, in all directions. you get such a, say, constant temperature. So if we were locked inside quickly flying rocket without any windows, yes? So due to Doppler phenomenon, this is electromagnetic waves with very low frequency, but due to, say, Doppler phenomenon, if you would fly quite high, then you would, this electromagnetic waves would change to temperature, infrared or optical or ultraviolet, or if you would increase the speed, then you would get Röntgen, for instance, rays, but they could be surely measurable inside the windowless rocket, yes? So people found the origin of this cosmic microwave background, Nobel Prize winner. And this is another, say, system, inertial, which can be, say, called reference inertial system, because we know in which way we would go. We are not addressed with respect to this cosmic microwave background. I suppose that I discovered this by myself, but later I found that due to Avril, that Bergman already wrote a paper about breakdown of the principle of relativity in 1970, so more than 50 years ago, yes. There is another example, which can be, this third inertial frame can be assigned to intergalactic gas or dust. There are about 10 protons on average in each cubic meter. In each cubic meter, you have 10 protons in the universe. Not here, there are billions of protons, yes, but in, say, intergalactic gas. And this also cannot be eliminated, yes. So if you would travel by high speed, then, and you would have some detector of particles, you would easily find that you are moving and not the neighborhood. Okay, so this system, inertial, cannot be ignored. And this means that there is some preferred inertial system, and this contradicts to principle of relativity. So now a few words about conclusions. So concerning this second, say, postulate about the constancy of speed of light, there are also many papers which, according to them, it is also problematic, this postulate, especially in high gravitational fields. Okay, so I presented 3 examples. The principle of relativity does not hold in the physical universe. Of course, in piece of paper, this is a beautiful theory, yes, but we should look for models, mathematical models, which describe our universe pretty well, not just that it is only beautiful theory on a piece of paper. Okay, so I will skip perhaps this. I didn't see any paper which would criticize, for instance, acoustic waves or theory of heat conduction or theory of elasticity, but there are really many papers criticizing theory of relativity. Of course, I know that it is the most celebrated theory, but at the same time, this is the most criticized theory, yes? So to show you a few examples, so there are, for instance, 2 myths about special relativity. Is special relativity, the special theory of relativity wrong? It was published in Nature. Another paper in Nature, the case against special relativity here. Is special relativity wrong? And Pavel Kroupa, dark matter crisis, falsification of the current standard model of cosmology. And here catalog of errors of both theories of relativity. Einstein's special relativity is absolutely on the controversies of special relativity, and so on and so on. This list is absolutely not complete, and I thank you for listening.
Thank you so much. And again, we have comments from senior lecturer in physics, Esko Keski-Vakkuri, please.
Okay, so thank you for this
Yeah.
summary of your ideas. I don't think I saw anything that convinces me that the principle of special relativity is wrong. I think that there were some misconceptions that what the principle of relativity really says that no inertial frame is fundamental, that any frame can be taken as a starting point, and then it provides transformations that you can now map observations in one frame into observations into other frame, but it doesn't tell you that if you compare observations between these different frames that they should be the same. So that's not what the principle of relativity says. And then, so all these things, when you add to the principle of relativity other things like the Doppler effect and things like that, that's not part of the...
Yes, it is not. Yes, of course. Yeah.
Okay, so that, as you know. Now, the one interesting thing is that I would be very surprised that if there's no experimental evidence for length modules.
Please give me the exact reference. If
I certainly look after your talk.
All right.
Given that the precision in measurements has increased so tremendously in the past 10 years or so, I think by now there should exist a measured experiment, but I'm not also aware of any. And then now these problems of GR, are they problems or are they just features of the theory? Like, okay, so there's no analytic solution for two bodies in GR for the motion of two bodies, but then again, if you go to Newton's theory, then there's no analytic solution for general motion of four bodies. So it's just a feature of the theory.
Even three bodies.
And then.
But we can estimate, sorry that I'm interrupting you.
Yeah.
We can estimate the modeling error, yes? If you have Newton theory, then we can estimate the modeling error. In Einstein equation, you cannot estimate the modeling error for more than one body, for more than two bodies, yes?
And then
two bodies.
Yeah, and well, that's right. So it's a feature of nonlinear theories, and then also, well, we don't have to look at, if you look at hydrodynamics, we also know that turbulence is not understood.
Well, of course.
It is of the theory, so it is what it is. And then this cosmic microwave background, now I think that's not really a preferred frame. Like if you discuss Newton's theory, which is invariant under Galilei transformation.
Yes, of course.
And so translation in space is a symmetry.
Yeah.
If you look at this room, obviously it's not symmetric under.
No,
space
of course.
So it's just that within a theory which has symmetries, there can be states that are not symmetric.
Yes, of course.
Just the feature that cosmic microwave background, same thing.
No, there are local fluctuations, yes, but if you travel with very high speed with respect to microwave background, you will easily find that it moves, that you move.
Yeah, but that's Doppler effect.
Sorry?
That's due to Doppler effect.
No Doppler effect, due to Doppler effect. Yes, of course.
It's not, I mean, again, it's observations can tell you something, but it's not really about the principle of relativity itself that says that in one frame things can look different than in another frame, but then you use the Lorentz transformations and other things to map the observations. But the principle of relativity doesn't say that. I mean, obviously, forget about relativity. If I would be moving in this room,
Yeah.
of course I can tell that I'm moving, even if space translation invariance tells me that my
Yeah.
frame is no different
Yes.
from your day.
Yes, but it is locally, but this is also globally. Globally and in any direction, in any distance on arbitrarily long
Yeah,
distance.
but if we have an infinite universe
Yeah.
filled with let's say,
With some medium, yes.
planets, I move in this lattice, and then invariances of Newton's theory would tell me that my frame should be the same as another frame, but I can tell that I'm moving because I simply see the planets moving. If I'm
Yes.
that's an infinite space. So
No.
so I didn't quite. Well, with all respect,
No.
it's good that it's always good.
But why Einstein equations have so many problems? Yes.
Well, because they are difficult equations, so they
Yes. Nobody can solve them. Only for one body. Yes.
well, we will be unemployed. It would be too
Great. Thank you for these comments. And we have time for some questions.
Thank you. Well, the Einstein's or relativity's first principle was a relativity principles. That means that either of the movers can consider to be at rest, and
Yes.
either does not know whether he is moving or not. But you said that there is a technique. If one is moving, he is moving against this cosmic microwave background.
Yes.
So, and the wavelength, depending whether it goes this direction, it is different whether it
Yes.
that direction.
Yes.
So, in real world, he can detect, can see whether he is moving or not.
Yes.
So,
Exactly.
so it means that the principle of relativity, either one can be considered to be at rest, and nobody knows whether it's moving or not. This does not hold.
Yes.
So it falsifies this principle of relativity, this postulate. That's all.
No, Einstein assumed that it is in vacuum. Maybe it is in this, I don't know. He assumed that it is a vacuum, but space is not like that, yes? He also, Einstein could not know about the existence of the cosmic microwave background because it was discovered 60 years later, yes? Yes, yes, as a mathematical model, it is perfect. This is perfect theory. But does it is there any sense to work on theories which do not describe our universe well? This is the problem. Of course, I have nothing about the theory. Theory is beautiful, but it does not describe our reality.
So perhaps I misunderstood, but it seemed to me that at one point you were saying we can easily see that that relativity is at odds with the facts, because if you had length contraction in the direction of motion, then we would be able to distinguish our frame of reference. We would see ovals traveling with us rather than circles, right? The circles.
Yes.
Well, when I was first learning about relativity, that was the kind of reaction I had, but it was quickly explained to me that the contraction is between frames of reference, not within the frame of reference. So there is no length contraction within the frame of reference, right? It's only a relation between frames.
Yes, exactly. Yes.
So what you're saying isn't correct. You will still have the indiscernibility of all frames of reference from within each frame of reference. I will not perceive the circles as ellipses because they do not contract within the frame of reference. The contraction is only a relation when someone else in a different frame of reference observes my motion, then relative to them, my ovals will be
Yes,
contracted.
yeah, yes,
But
yeah.
I will not see that, so it cannot
No, yes.
the role of disconfirmation that you said it could play. So just wanted to make that point because I'm sure 90% of the people in the room are having the same thought, and it should be said.
No, I agree. If you substitute just to Lorentz transformation some high velocity, you get that the contraction or the Lorentz factor is gamma, for instance, 2, and the observer which sits at the beginning of this right, say, inertial system will see everything is deformed, so he must be sure that he is not at rest. Yes, he's not at rest. Of course, this figure can be, say, it is only, say, idealization. These blue dots can have different, say, sizes. You can consider three-dimensional space and so on. Yes, this is only, say, illustrative
Let me put it this way. If you were right, then you would be contradicting your answer to the previous question, which is you said there has been no experimental evidence
Yes.
of length contraction. So you can't have it both ways.
Yeah, no, of
Either
course, no,
there has
of
never
course,
been
of
an
course.
observation of length contraction,
course.
or there has been,
Yes,
which
I
would
agree.
refute. But I think there has not been any. No one has ever observed within their frame of reference relativistic length contraction,
Yeah.
and that is both consistent. That's exactly what you would expect given the theory of relativity. You would not. Einstein never said you would observe length contraction within your own frame of reference. That's a misunderstanding of his theory.
Yeah, yes, okay.
Okay, all right.
So here, if I just see something like in the left or see something like the right, what
Yeah.
the principle of relativity says that none of these. Well, I could ask you, what is more fundamental, seeing the grid on the left or seeing the grid on the right? Is one of these observations somehow more favorable than the other observation? And it's not. So that's the principle of relativity.
Our time is up. Let us thank all the speakers and our commentator. And there should be coffee in the hallway, and we will continue with parallel sessions at 4 o'clock.